I have a cold, so hopefully you'll be able to hear me. I have a cough drop, tea, and beer, so I will array these around the stage. I also had to teach for 3 hours today, so the voice is going out. All right, let's see if this works. So I'm going to talk to you about a time in the universe known as Reionization, and the title of the talk is Reionization, a cosmic detective game, sort of a whodunit tale of what was responsible behind this period in the universe that we'll talk about. So something has been ionizing the gas in the universe. You shall be very scared. It could get you. Maybe, maybe not. So what if I was to tell you that over 1 billion years ago, the intergalactic medium, this is the space that fills the universe between galaxies, it's full of gas. That gas transitioned from a neutral state, where all of the protons had their electrons, to an ionized state, where all of the protons lost their electrons. What if I was to tell you that happened? Would you be scared? You should be scared, because it did happen. All right, so this is the mystery we're going to talk about. We don't necessarily know why, but we have a lot of ideas, more ideas than I have time to talk about, but we'll talk about a few of them. So let's go through a bit of the details. So when did this happen? This happened sometime in the first billion years, after the Big Bang. Okay, does anybody know how old the universe is right now? To the second decimal place, please. So our best guess right now is very close, 13.82 billion years. Okay, so we're talking about almost 13 billion years into the past, the first billion years after the Big Bang, where the IGN, the intergalactic medium, this is the hydrogen and some helium that fills the space between galaxies. It was the source of the filaments, those cosmic filaments that Dr. Jogi showed in the last talk. Why? Physics. We'll talk about the physics just a little bit, but we'll talk about the physics of why this happens, why these photons lost their electrons, and who. This is the real mystery. Okay, we want to figure out what was actually responsible, what was providing the energy behind this time in the universe called reionization. Okay, so it's a whodunit tale. I didn't have time to put cool murder mystery sound effects in this, so we'll have to imagine those in our head. All right, so first the physics. What is ionization? So we'll stick to the hydrogen atom. It's the most abundant atom in the universe. It's what fills most of the IGN. Hydrogen, when it's left to its lonesome, is a proton surrounded by a single electron. Okay, that electron can do funny things. That electron can exist in a bunch of different energy levels. Okay, so when that electron is left to its own devices, it wants to be where you are all right now in your ground state, right? If you're standing, you all want to sit down, maybe even lay down. If you can, don't do that here, probably. So the electron wants to exist in its ground state right here. We give it a weird name, the n equals 1 level. Okay. So to excite the electron, to move it to another energy level, we can do it in a variety of ways, but the most common way is through the absorption of a photon, so a particle of light. So if a particle of light hits a hydrogen atom, it can actually excite that electron. And not just any photon, it has to have a very specific energy, a specific energy that is equal to the energy difference between these two levels. That's all well and good. I'm going to show you this really complicated looking diagram. You actually don't have to worry about any of this because we're going to talk about ionization. So electrons can go from the ground state to any of these other states, but if a photon comes in with enough energy, and for the hydrogen atom, that's a very specific amount of 13.6 electron volts. That corresponds to an ultraviolet photon, one that's just a little bit bluer than our eye can see. It can actually ionize that electron. And I prepared a very, very detailed simulation to show you what that looks like. Okay, so here is our hydrogen atom. I actually didn't know this until I put this up, that this has 2 electrons. Ignore that. There's just 1 electron. Now, radiation is coming in, ionizing photons. It's very energetic, and poof, it's gone. Okay. So now you all understand ionization. It's the process of kicking electrons off of atoms. Hydrogen only has 1 electron, so it just has to lose its 1 electron. All right, so that's ionization. Okay, so let's go through, actually we're going to do a few primer things. First I'm going to talk to you about Redshift, which we got a brief introduction in the last talk, and then I'll sort of walk you through the timeline of the universe. All right, so this is a really old plot. It's actually wrong, but that's okay. This was a plot that Edwin Hubble, have you all heard of Edwin Hubble? He was so cool, we named a telescope after him, that he made almost 100 years ago. This is the discovery that the universe was expanding. So this x-axis, which you can't read, this is distance. The y-axis is velocity. So as we move farther and farther away from the Earth, or from our galaxy, really, galaxies are moving faster and faster away from us. So the universe is expanding. Okay, we have to remember one other thing from middle school, maybe high school, maybe my class this morning where we talked about it, which is the Doppler effect. Okay, so when things move towards you, the light waves get squished and they appear bluer than they normally would be. When things are moving away from you, the light waves get stretched and they look redder. So everything essentially is moving away from us. So does everything look redder or bluer than otherwise would be? Redder, right. So everything is redshifted with the exception of Andromeda. Trivia question. The nearest galaxy to us, and it's actually a trivia question for the last talk, but I'm going to do it anyways. The nearest large galaxy to us, Andromeda and the Milky Way, will actually collide in 4 billion years. And what kind of galaxy will we make? Elliptical. Good. Very good. All right. But everything that's farther away than Andromeda mostly is moving away from us. It's expanding. And so I'm going to try and stick to units of time when I'm talking about different eras in the universe, but I may slip up and revert to redshift. And so we, in the know, label galaxies by their redshift number. So bigger redshift number means farther away. Today, we're all at redshift 0. Congratulations, you've made it. You're redshift 0. The most distant galaxies are at redshifts sort of 8 to 10 or so. And we're seeing those galaxies at a time less than 1 billion years since the Big Bang. And so that's what this right-hand column is, time since the Big Bang. Here we are. I only put 1 decimal place. A slacker, I'm sorry. As we go back in time, redshift 1, we're already more than halfway back towards the Big Bang. We're going to be talking about redshifts greater than 6. So within the first billion years, you might see redshift on an axis. I apologize. But now you have a brief introduction of what that is. All right. So let's talk about a brief history of the universe. This is a diagram, and I'm just going to label a few different points in time in this diagram. So the universe started with the... said that too fast. Can't get a drink of my beer. All right. Hey, you're right. Oh, that didn't show up. All right, Big Bang, or the Big, as it were. So the universe started with a Big Bang here on this plot here. Okay, that happened 13.82 billion years ago. Okay. After that, immediately after that, came the topic of the third talk, inflation. So I'm basically not going to talk about that because I'm pretty sure we're going to get that later. That made the universe get real big real fast. Okay? Solves a lot of problems. We think it happened. We don't have a lot of evidence, but we think it happened. All right. A little while later, about 370,000 years after the Big Bang, came a time known as recombination. We should actually call this combination. It was the first time that protons and electrons combined to make neutral atoms. We call it recombination. I don't know why. It had never happened before, so it's really just combination, but we call it recombination. And when that happened, all of the residual energy from the Big Bang, which is in the form of light, was able to freely stream through the universe to our telescopes. How many of you have seen a picture that looks like this at the top? Does anybody know what this is called? Yeah, smart audience. Cosmic microwave background. So this is like a baby picture of the universe. This shows us the pattern of overdense regions in red and underdense regions in blue that were there in the early universe. So this is actually a picture of the inside of a sphere sort of flattened out on the page for you to see. So it's a baby picture of the universe. Oh, I spoiled it. So that's 370,000 years after the Big Bang. Okay. Then nothing happened for a while. All right, and we call this the Dark Ages. Okay. Seriously. It's not a joke. All right, so during this time, the universe was dark. All right. During this time, the gas started out being really hot. So when the cosmic microwave background radiation was emitted, the universe was fairly warm, like the surface temperature of a star warm. And it takes time for gas to cool. We need gas to cool so it can dense and collapse into stars. Stars are bright. Those are the things we want to see. We don't know how long the Dark Ages lasted. We think on the order of 100 million years, 200 million years. It can't be more than 500 million years because the most distant galaxy we've seen today with Hubble comes from a time about 500 million years after the Big Bang. So the Dark Ages had to be shorter than that. We don't know. We're simulating it, including lots of people here at UT. We're trying to work hard at it, figure it out. When the Dark Ages ended, they ended with the first stars to form in the universe, which we call population 3 stars, or the first stars. Here is one of many beautiful simulations you can find on the internet about what a first star should look like. And this, we think, again, somewhere between 1 to 200 million years after the Big Bang. That's when gas could finally cool and condense enough to form the first stars. Okay, after the first stars, okay, so first stars form in isolation. Maybe you form a few, but you're not forming thousands of stars like you would form in a galaxy. But soon after that, you do form thousands of stars like you would form in a galaxy, and we call that the first galaxies. Again, we don't know when it was, but probably something like 200 to 300 million years after the Big Bang. Maybe they look like this. This is a nice movie showing, very similar to the movies you saw in the last talk, galaxies forming early on. Okay, so now we've made it to about 300 million years after the Big Bang, and then there's a lot of stuff that happens. We're going to skip it. Today is 13.8 billion years later. All right? So we're all caught up. We all know how the universe worked. Lots of stuff happened in between them, but that's fine. The early on part is pretty cool. So what did reionization look like? This is the pretty video part of the talk. There will be 3 of them, okay? So here's one. by Marcelo Alvarez, who was a graduate student at UT. Is that right? Graduate student at UT. And what, I should actually say what this is. So it's going to start very dark. That is the Dark Ages, okay? As the first luminous sources appeared in the universe, whatever they were, maybe it was galaxies, we'll get to that, all right? They were emitting lots of radiation that ionized the gas. They popped those electrons off. The hydrogen atom, ionized gas is going to be colored in blue. And so you see it's kind of very patchy. Its star formation is clustered, okay? So as you start to make these ionized bubbles, more and more stars or galaxies or AGN or other things we're going to talk about, we don't know yet. Remember, it's a whodunit case. I don't want to spoil it. They grow and grow and grow. Eventually, these bubbles start to merge, and you'll get this period of overlap. Okay, now we're maybe 50% ionized by volume, maybe, more or less. Okay, it's keeping going, keeping going. Whatever is making the energy keeps going, and eventually we'll complete this process of ionization. All right, I'm actually going to skip to another video where we get to fly through this box, okay, which is pretty cool. So here we are. Dark Ages, you can barely see anything. The first sources start to light up. And you will actually see these ionized regions grow. It takes a minute to get really exciting. Maybe 2 minutes. It's almost there. Can you spot any ionized regions? There are some. There's something in there. This simulation actually doesn't really show you what's in there doing the ionizing. Well, again, we'll talk about that. But as you can see, those regions are getting bigger and bigger. They start to overlap. This little wall of neutral gas here will eventually break down. We're about to enter a really large ionized cavity. Ooh, I don't know what that is. That could be the ionizing source. Somebody grab it. Okay, and then you'll see the end of reionization goes by really quickly. A lot of these movies are on YouTube. They're very cool. I learned I was too old to understand how to download things from YouTube, but luckily Brandon was able to help me figure that out. All right, and these sort of last little wisps of things are going by. So we're at about probably 1 billion years after the Big Bang now, and these are going to go away pretty quickly. Okay, now we have a universe that is fully ionized. All the gas has lost its electrons. All right, I'm going to show you one more movie, just because it's a different color scheme. Okay. And this is from a group at Georgia Tech led by John Wise, and I was actually on Twitter before the thing tonight and saw that this movie won Best Visualization at a supercomputing conference today. So I was almost going to skip it, but now I'm not. So here we can see these ionized bubbles here. We're going to fly around the box. It's pretty cool. In this one, time is not going by quite as fast, so it's a little bit hard to see the ionization changing. But what you do see is that these bubbles kind of are not uniform. The universe is very clustered. There's a lot of stuff here, not so much going on over there. All right, so I'm going to end the pretty video portion of the talk, and we'll get to some boring science plots. Sorry. All right, so what do we actually know? So we know a lot to make those videos, so I'll walk you through the observational constraints. We've sort of learned a lot about reionization over the past few decades. The first thing is we can actually measure the fraction of gas which is neutral, because that's cool, because if you measure that fraction to be 0, then the universe is fully ionized. If you measure it to be 1, then it's all neutral, okay? And you can measure how that fraction changes with time, and you can track this process of reionization. And the way we do this is by actually looking at really distant quasars. Quasars are supermassive black holes that are actively eating a lot of gas, and they get really, really bright, and they act like big cosmic flashlights illuminating the gas between galaxies. That's kind of what this is illustrating here. That's what that's supposed to be. Don't worry too much about that. But what we've learned from these measurements is that the intergalactic medium is ionized today. It was ionized yesterday. It was ionized 1 billion years ago. It was ionized all the way out to a point about 1 billion years from the Big Bang. Okay, we can tell that very conclusively. At greater times than that, or closer to the Big Bang than that, it may be getting more neutral, but it's really hard to tell because we stopped finding quasars, because you need time for quasars to grow as well. And so we've lost our cosmic flashlights. But a really cool thing that the GMT will be able to do is follow up these extremely bright events known as gamma ray bursts. Gamma ray bursts are involved with merging stars and exploding stars, and they're really bright, but only for like a few minutes or a few hours, depending on the event. But the GMT will be able to very quickly swivel around and look at these things and take spectra like this and measure the neutral fraction into the very distant universe. But from what we can tell today, reionization happened some point in the first billion years. The second thing we can do is we can take the temperature of the intergalactic medium. And by temperature, what I really mean is we can sort of measure how many ionizing photons are out there. And it's actually through really similar measurements as this. And what we found is that there appear to be enough ionizing photons to accomplish reionization, which is good because we can tell reionization happened, so there's no discrepancy there, but like only just barely. There were barely enough ionizing photons to do it. So whatever source you want to invent to accomplish reionization, you can't invent something that's going to make like 10 times too many or 20 times too many ionizing photons. You need to have like just enough. It's kind of a cosmic coincidence. And the third thing we can do, I called it skewering the universe. That's looking back along lines of sight to the cosmic microwave background. And you can actually count the electrons along the line of sight. And that's another independent measure of when the universe got reionized. Okay? If you see a lot of electrons, that means that it must have been reionized really early, because you're seeing electrons basically all the way back to the Big Bang. If you're not seeing too many, it must have been ionized pretty late. And basically what we find from this, from the Planck satellite, which made this great image, is that this is consistent with reionization ending around 1 billion years after the Big Bang, which is consistent with this data here. And it probably didn't start much earlier than 500 million years, which is when we're seeing some of those earliest galaxies. So to summarize from this, whatever is doing reionization can't start too early, it can't finish too late, it also can't overshoot the number of ionizing photons. So it's a really, really tight box to fit into for whatever we're talking about. Okay, so let's run through the culprits, the suspects. So galaxies. Could it have been galaxies? Maybe. No? All right. Could it have been accreting supermassive black holes? Also maybe. Could it have been exotic unknowns? Exotic unknowns. And I'll run through a few of those really quickly because I know I'm going long. All right, so let's talk about galaxies. So how do galaxies make ionizing photons? Galaxies make ionizing photons by making stars. So if you form new stars, you're going to form stars of all masses, but some of those stars will be very massive. Very massive stars are really hot. Really hot stars produce lots of ionizing photons capable of knocking off those electrons. All right, and as it turns out, galaxies in the distant universe are forming stars like mad. They're forming lots of stars. They're forming lots of ionizing photons. And so this is a really promising culprit or suspect, right, for reionization. The key thing, and I'll come back to this, is just because these stars make ionizing photons doesn't mean that the photons make it out of the galaxies, because galaxies also have neutral hydrogen gas, and that gas can absorb these photons. So it could be like a cosmic tragedy that all of these galaxies make all of these ionizing photons, and they never make it out to fulfill their destiny of achieving reionization. All right, so we don't know, and I'll come back to that. We call this the escape fraction. What fraction of those photons that are made make it out? All right. So one thing I wanted to tell you, though, is to figure out whether there is enough star formation in galaxies, we just count up all the galaxies in the distant universe. And this is something that myself and my collaborators have been involved in for a while, using beautiful images such as these taken by the, what telescope? Hubble Space Telescope. Does anybody know what this is? Hubble Ultra Deep Field, now hanging on the wall in my office, which is super awesome. The Hubble Ultra Deep Field. So we can count up the galaxies at different times and figure out how many stars are forming, and from there figure out how many photons there are. And this is a boring plot from a science paper I wrote, but this is showing basically the number of stars forming. This is actually a very similar plot to the one that Sharda showed, the McDowell-Dickinson plot. The x-axis is a little different. But there are lots of stars forming early on. And so you say, okay, if I take all those stars and I make some assumption about what fraction of those photons are escaping, can I make reionization happen? And it turns out the answer is yes. So this purple line is showing, I'm going to show you a bunch of in preparation plots from a paper. Please don't scoop me. I'm not teaching next semester, so maybe I'll be able to finish the paper, so don't scoop me before then. All right. So this is showing ionized fraction versus time after the Big Bang. Very early on, nothing's ionized. By 1 billion years after the Big Bang, we did it. We ionized the universe with galaxies and galaxies alone, okay? But we did it by assuming a fraction, an escape fraction of 13%, okay? So something like 1 out of every 7 ionizing photons escapes a galaxy. It's pretty conservative, right? Seems maybe okay, all right? I'm definitely not going to talk about this again and tell you this is too high, all right? So let's move on and let's talk about accreting supermassive black holes. Okay, so these are black holes in the centers of galaxies that accrete lots of gas, they get really hot, and they can also emit lots of ionizing photons. People have been really down on this idea because when we look at star formation versus time, we see that it does decrease as you go to early times, but it's relatively shallow. When you look at black hole activity versus time, it sort of falls off a cliff, okay? But these measurements in the very distant universe are quite uncertain. This is just one model. There are other models where maybe it doesn't fall off so steeply. So maybe these active black holes, or we call them active galactic nuclei, or AGN, maybe they also played a role. And finally, the exotic unknowns. There are a lot of them. I just made up 3 of them, ideas that people have had. One are these crazy things called dark stars, where in the early universe you could form extremely massive stars, stars that are 1,000, 10,000, even 100,000 times the mass of our sun, that are actually supported by dark matter for a short time. And they could be really hot, which would make a lot of ionizing photons, maybe. Annihilating dark matter. Dark matter itself, one theory about dark matter is that when two dark matter particles get close together, they annihilate and turn into energy, gamma rays, which would be ionizing photons. They could do it, maybe. Or population 3 stars. These had to have happened at some point in the early universe, but the current idea is that there probably were not enough of them to contribute significantly. So there are all these other ideas floating around, but when I think about this, I really only like to consider these if I can really rule out everything else. So I'm going to talk about whether we can do it just with galaxies and maybe a splash of black holes. Okay. So could it be galaxies? All right, this is an image taken of a galaxy. It's actually a bunch of galaxies all stacked together. They're really bright. They're heavily star-forming galaxies. This is an image taken in sort of a blue filter, so we're kind of seeing the blue light from this galaxy. This is an image of those same galaxies looking at the wavelengths where we would expect to see the ionizing photons. So if any of them are escaping, we should see them here. And do you see anything? No. And so it doesn't mean that 0 of them are escaping, but whatever it is are below our detection limit. So what this tells us is that escape fraction is probably not 13% on average. It's probably much lower. Okay, and so this is the result of what you try to do if you take galaxies, but you make their escape fractions be really low, like 2% or something, and you try and reionize the universe. So we basically want to get to 1. We want to get to the top of the plot by redshift 6. Blue are the results from this particular analysis I'm showing with only galaxies, and it doesn't work. Okay, it doesn't reionize until like redshift 4. It's way too late. We know that's not true. So if we don't have any AGNs, but we use realistic escape fractions, it's an abject failure. That's why my paper's not done, because I didn't want to end on that note. So what can we do? Well, we can add in AGNs. We can say, hey, let's add in some black holes. Not too many, just a splash. Let's see what happens. And it turns out that we can make it work. There it is. And here we go. We get to 1 by redshift 6. And the key point I want to make here is galaxies are actually doing the bulk of the work. This is a figure showing the relative importance of galaxies to AGNs as a function of redshift. I knew I'd do it with redshift. So these are very early times. These are later times. Above the gray line, galaxies are dominating. So galaxies are basically doing most of the legwork. Galaxies get reionization almost complete. AGNs pick up just at the end to finish it. Okay, so it looks like it was a team effort. Galaxies started off, AGNs sort of tag in and finish it off. So is it case closed? Okay, was it a team effort? Do we need to arrest both of them, galaxies and AGN? Well, I wish I could convince you that were the case, but I would be lying because this is just a model. This is a model that fits all the data, but we don't know if it's true. But one thing that model does do is it makes a lot of predictions, and I'll run through a few of those for you. First, this model predicts that reionization starts pretty early, that the universe, actually go back really quick, the universe was actually significantly ionized by redshift of 10. Remember, this is the first galaxy we can see. And if the universe is significantly ionized earlier than that, there must have been galaxies around to power that ionization, which is really cool. So we should see lots of galaxies at redshift greater than 10, which will be awesome and will keep me busy for a long time. The second thing is that AGNs, these really massive accreting black holes, should exist at high redshifts. Maybe not super common, but we should be able to find them. Okay? And the last thing is that decently sized ionized bubbles should also exist out to redshift of 10. It's not just a tiny fraction of the universe that's ionized, it's like 40%. So we should be able to go see those bubbles. All right. So these are some predictions. I wish I could tell you that we could test these predictions today. Actually, this one at the bottom, we're trying to test. Rebecca Larson, I don't remember her nickname or whatever. She's sitting in the back somewhere. She helps run this. She is working on this part of the project. The other two, we don't have a telescope to do yet, but we will in 2019 with this thing. Okay, does anybody remember what this is called? James Webb Space Telescope. Yeah, I like it. So this is showing the second most terrifying thing about JWST. The first most terrifying thing is we have to launch it on a rocket into space. Okay, this is an unmanned rocket, no people on this rocket, so it has to not blow up. Nobody joke about it blowing up. But then, because it has to fit into a rocket, it has to be all folded up. And then when it gets into space, it has to unfold. Okay? There's no people on there. We used to joke that we're going to like send a graduate student on there to like help it unfold, and then they would get their PhD thesis as long as they made it unfold. No, we won't do that unless there are any volunteers. I don't know if there are any volunteers. So it's got a lot of work to do. Every single moving mechanism is triply redundant. So it can fail twice, and we'll still be okay. Fail 3 times, we've just wasted $9 billion. All right. Oh, yes. But this will revolutionize essentially all areas of astronomy, so I think it's worth it. It's almost there. It's got to fold out the secondary mirror and fold out the ears, okay? And so this is going to launch in spring of 2019. It was October of 2018, but they decided they wanted just a little bit more time to not mess it up, which seems like a good idea to me. So it'll still launch in less than 2 years. Does anybody know where this telescope is right now? It is in Houston. It is in Chamber A, where the Apollo astronauts trained. It just finished its last cryogenic optical test, and the mirror is great. It's ready to go. No problems like Hubble had. How many of you remember that Hubble had a problem with its mirror? Yeah. This is going a million miles away. We can't send astronauts to go fix it. So it is good. Okay. It's ready to have the whole spacecraft strapped onto it and sent on its way to French Guiana in South America, where it will launch in spring of 2019. Okay. So, as Sharda alluded to, selections were recently made for some of the early release science programs. So these are some of the first observations to be done with the Webb, and undoubtedly some of them will be able to verify some of these predictions I've talked about. And in fact, one of them would be the Cosmic Evolution Early Release Science Survey that we are very familiar with here at UT. And so this survey, which is so tightly constrained that it can only be done in 1 week in December of 2019, so the launch cannot slip anymore. We have a lot of work to do. It's going to do a lot of stuff. I don't have time to talk about it. It's going to take lots of cool images. It's going to take lots of cool spectra, and it will be capable of finding galaxies out to redshifts of 12, maybe even 13. It will identify lurking AGNs if they're hiding there, and lots of cool stuff. These are some images. This is Hubble and Spitzer trying to see redshift 10 galaxies. You can barely see it. This is Webb. Trust me, that's a really good detection. I know it may not look impressive to you, but that's good. And we're going to see lots of cool spectra, just lots of stuff we can't even imagine about doing right now. So this is going to be very exciting. Stay tuned. As Sharda mentioned, we have, of the 13 accepted programs, we're involved in 5 of them, including a couple other Galaxy ones, so it's going to be a very exciting time. Thank you.
Thank you, Notorious LAE. So we have some time for some questions. Oh my goodness, we got one right here.
You gotta say it loud. Okay, all right.
It's little Notorious LAE asking a question.
That is my 7-year-old son right there, who's asking me the hard questions. So how can we see things that are 13 billion years old when we are here today in 2017, right? And the answer is, if that was not your question, you can ask again after. The answer is that light travels at a certain speed. I said this in my class this morning. If light traveled instantaneously, if it could get from one side of the universe to another, galaxy evolution would be dead, because we would only always see things as they are today. But because light travels at a certain finite speed, when we look some distance away, we don't see that galaxy as it is now. We see it as it is in the past. So when we look at the Andromeda galaxy, we're not seeing it as it is today. We're seeing it as it was 2 million years ago, which is actually not a lot of time in the universe. But we can now look billions and billions of light years away and see things like what they looked like very early on in the universe. Cool? All right.
Anyone in the balcony? Come on.
I can't even see it.
Guess not. Okay, right there, sir.
Yeah, before recombination, when everything was ionized, the universe was opaque, right?
That's right.
So with reionization, did that make the universe more opaque again? And if so, to what extent?
Yeah, that's a great question. So before recombination, the universe was a bunch of protons and electrons, and photons scatter off of electrons, and that's why we can't really see into that time in the universe. We can only see after the electrons combine with protons. And so this is an excellent question. After reionization, we have a bunch of electrons again. Why is the universe not opaque? And the answer is the density. The universe is much, 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 much larger a billion years after the Big Bang than it was just 400,000 years after the Big Bang. So the density of electrons is much, 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 much less. They still can scatter photons, and that's actually how we count the photons in that third measurement, that cosmic microwave background measurement I was talking about. There was a question here, but
Right in front.
Yeah, so that was kind of my
Oh, okay.
question too, is once it gets ionized where the protons and electrons get separated, what happens to those?
Ooh, good question. So they can recombine, but what we have found is that after reionization happens, the gas stays ionized. So there's enough energy being pumped out of these, mostly galaxies, maybe AGNs, to keep them ionized. So if electron and proton recombine, zap, immediately they'll get separated again by a high energy photon.
So they're out there, they're transparent, you can see through that?
That's right, yeah.
So what forms of stars and stuff?
Ooh, good question. So when we say the universe is reionized, that's actually not correct. It's sorry, thank you. The question was, how are we forming stars if all the gas is ionized? And the answer is it's the gas between galaxies that's ionized, but gas inside of galaxies is actually able to cool by first grabbing its electron, forming a hydrogen atom, and then often grabbing another hydrogen atom and forming a molecule and getting really, really cold and dense. So inside of galaxies, the gas is not all ionized. Some of it is, but not all of it.
One last question right there.
Do you have an approximate percentage of what percentage of the mass is ionized versus non-ionized?
What percentage of the mass is ionized in the universe? Oh my goodness, that is a really good question. I want to say on the order of a half, like closer to a half, like half the gas is in between galaxies. There's lots of mass in between galaxies. So let's go with a half. And if you want to correct me, people over here, do it after I'm off the stage.
Yeah. Let's talk during the intermission. So let's thank Notorious LAE again.